Okay, let's begin with the preparation. Before actually using the canvas, there needs to do some preparation. For the clock, PLL modeling is required. We do not design the PLL hard macro itself. Canvas only designed the PLL controller, so you need to define PLL control signals as register description format. Here we have PLL 1000 as an example. It has this kind of control signals. It also has F-out calculation formula based on the control signals and lock time spec. And let's make one more PLL here. Let's rename it to PLL 2000. And let's copy and paste the control signals like this. You can add or remove. You can compose these control signals as you want. And let's copy the calculation formula and lock time spec and done. Now, another type of PLL is registered. This can be selected in the clock diagram. And the clock comp is to replace the core part of clock component, mux and divider. Clock component consists of controller part and the function core part. So if you want to use your own legacy design or hardening components for the function core part, you can describe it in here. This is not essential because Canvas already provides both parts and it's complete design. But anyway, if you want to use it, you can do that. And this is generic definition. This is for removing process dependency. This is an example of generic file. Within the Canvas generated RTL, there are hard-coded parts marked as don't touch instance. The cell names for this part can be different depending on the process, so generic modules are used to remove the process dependency at the RTL level. In this example, a cell name end2 demo is used, but in the actual project, the standard cell library information of that project should be defined into the Canvas in advance. It will be replaced with the real cell name from the corresponding process library. And if the defined use ITDA behavior generic is activated, logic for operation part are used. So RTL level verification should be done with this define. If this define is not activated, then this part is used with the actual standard cell for the target process. So synthesis and layout should proceed in this way. Discrete clock and exception is used to generate SDC. SDC should point out the real hierarchy path of the cell, so it should be defined here first. And UPF. This is to input VDD, ground, and voltage information of hard macros, which will be used in UPF diagram. Here we have two examples, hard macros, PLL, PCIe, and they have a couple of VDDs and ground like this. Let's make one more. Let's rename it to like PLL 2000. And let's copy and paste all of it. You can add more VDD and ground here like this. Let's rename it to DVD 85 and done. Now we have another PLL. This can be selected in the UPF diagram. And the DFT, HMIF, this is hard macro interface. This is to input the boundary information of hard macros, which will be used in HMIF. Here we have PLL and PCIe and their boundary information like this. Also, you can add or remove like this, just like working with the Excel to make proper boundary information. And this is path control information used for GPIO controller. GPIO normally have these kind of control signals: pull up, pull down, drive strengths, input enable, output enable, etc. Also, you can add or remove as you want. This can be selected in the DFT MUX diagram.